Hi guys, in this video we will introduce the second order system.
A general model of a mechanical second order system consists of a spring and a damper. The equation of motion is shown here. If we apply the Laplace transformation and define two-parameter natural frequency and damping ratio in this form, we can get the transfer function of our second order system. According to the different value of the damping ratio, we can classify the response in underdamped, critical damped, and overdamped cases. And now we would like to use a ballet as our second order system, and we will use three inputs: the impulse, step, and sinusoid force input to illustrate the system.
We will first focus on the impulse response of the system. The output will simply be like this, and the roots are actually depending on the damping ratio. So there are only three cases. The first one is the overdamped case, where xi is greater than 1 and we have two real distinct roots. The second case is the underdamped case, where xi is between 0 and 1 and the roots are shown in the complex plane. The third case is the undamped case, where xi equals 0 and we have two pure imaginary roots. Now let's look more closely on how the damping ratio affects the impulse response using Mathematica. We first solve the second order system and then plot it. To better illustrate, we set natural frequency to 1. When xi equals 0, it's pure oscillation, and when xi is between 0 and 1, the response has oscillation and exponential decay as well. Then for xi greater than 1, the response becomes pure exponential decay.
The input to our second order system is a unit step force, look like this, and we take Laplace transform to it, it's 1 over s. I will focus on the parameter cosine in our transfer function, the case when cosine is from 0 to 1, the underdamped case. And now let's look at the output yt in mathematics. There are two important calculus. One is maximum overshoot MP, which is the difference between the first peak amplitude and the steady state amplitude. The other is 100% rest time, which is the time to get to the first peak. Let's see how will these two calculus change along different cosine. In the animation, n represents cosine which changes from 0 to 1. To see more clear relationship, we can look at this plot. On the direction of line, cosine increases. We can see maximum overshoot decreases and 100% rest time increases as cosine increases.
If I give a sinusoid force input to the second order system, let's see what happens. Let's see the response of our second order system to the sinusoid force input ft. We firstly do some basic change of variables that we can get the equation 1. Then we assume that x is in this form, and we derive the first and second order derivative of x. Then we do a little bit math, and we can get the final result a1. With bounded inputs, the response goes to infinity. This is called the resonance. One of the most famous examples, which is shown here, is the collapse of the bridge of the Tacoma River. We can see that the bridge collapsed. We are the future engineers. We should be careful about this phenomenon. For the ballet, if we apply the force input and the resonance happens, the ballet will become bigger and bigger and finally blows up. Hey dude, are you okay?